Welcome to today's problem walkthrough. We'll be tackling problem number 2154, keep multiplying found values by 2. In this session, we'll explore the problem requirements, consider various approaches to solve it, and analyze their efficiency. Let's dive in and break it down step by step. The problem is called keep multiplying found values by 2. In this problem, you are given an integer array called nums and another integer called original. Your task is to repeatedly check if the value of original exists in the array nums. If it does, you multiply original by 2 and continue this process until original can no longer be found in the array. Once this condition is met, the process stops, and you return the final value of original. The input consists of the array nums and the integer original, with constraints ensuring that the length of nums is between 1 and 1000, and the values in nums and original are all positive integers between 1 and 10,000. The output is a single integer representing the final value of original after completing the operations. To understand this better, let's look at the first example. Here, nums is 5, 3, 6, 1, 12, and original is 3. Start with original equals 3. Since 3 is in the array, we multiply it by 2, so original becomes 3 * 2 equals 6. Next, since 6 is also in the array, we again multiply it by 2, and original becomes 6 * 2 equals 12. Continuing, 12 is found in the array, so we multiply by 2 once more, making original is equal to 12 times 2 equals 24. At this point, 24 is not in the array, so the process stops. The final value of original is 24, which is the output. Now consider another example where nums is 2, 7, 9, and original is 4. Start with original equals 4. In this case, since 4 is not present in the array nums, the process stops immediately. There is no multiplication, and the final value of original remains 4. This demonstrates that if the initial value of original is not in the array, the operations do not proceed, and the output is simply the initial value of original. Let's look at one more example. Here, nums is 1, 16, 4, 2, 8, and original is 2. Start with original equals 2. Since 2 is in the array, we multiply it by 2, so original is equal to 2 times 2 equals 4. Next, 4 is in the array, so we multiply again, making original is equal to 4 times 2 equals 8. Continuing, 8 is in the array, so we multiply by 2 once more, and original is equal to 8 times 2 equals 16. Finally, 16 is also in the array, so we multiply again, resulting in original is equal to 16 times 2 equals 32. At this point, 32 is not in the array, so the process stops. The final value of original is 32. This example demonstrates how original can grow significantly when multiple doubling steps are possible. When considering edge cases, there are a few scenarios to keep in mind. First, if the initial value of original is not in the array nums, the output will simply be the value of original as no operations will be performed. Second, if nums contains duplicate values, they do not affect the process since duplicates do not change the outcome. Finally, if the array nums contains values that allow original to keep doubling endlessly within the constraints, the result will reach the largest possible value that can be achieved within the bounds of nums and original. These considerations ensure the problem behaves consistently across different inputs. To begin solving this problem, we first consider the brute force approach. The idea here is straightforward: start with the value of original and continue multiplying it by 2 as long as it exists in the nums array. You can implement this using a simple while loop where you repeatedly check if original is in nums using the in operator. If it is, you double the value of original. If it isn't, you exit the loop and return the current value of original. While this approach is simple to understand, it has some inefficiencies. Checking if original exists in the array takes n time, and since original doubles with each iteration, the loop runs approximately log original times. This means the overall time complexity becomes n * log original, which can be slow for larger inputs. To address this inefficiency, we can consider an optimized approach using a hash set. In the optimized approach, we use a hash set to improve lookup times. A hash set allows us to check for membership in O1 average time, as opposed to O(n) with an array. The first step is to convert the nums array into a hash set. Once the data is in this format, the process remains the same. Start with original, and while original exists in the hash set, multiply it by 2. The key difference here is that checking membership if original in nums_set is much faster. Converting the array to a hash set initially takes O(n), and the subsequent membership checks are O(1). Since the loop runs approximately log original times, the overall time complexity improves to O(n) plus log original. This makes the hash set approach significantly faster for larger arrays. Additionally, while there's a small trade-off in space due to the hash set, the performance gain is usually worth it. Another possible solution involves sorting the array, which we'll discuss next. When comparing these approaches, it becomes evident why the hash set approach is the most efficient solution for this problem. The brute force method, while simple, suffers from repeated O(n) membership checks, making it less suitable for larger datasets. Sorting the array offers an alternative, but it introduces an O(n)*log(n) overhead due to the sorting step, and the subsequent membership checks are still less efficient than the O(1) lookups provided by a hash set. Since this problem doesn't require the array to be sorted for other purposes, the sorting approach adds unnecessary complexity. The hash set approach strikes the right balance between time and space efficiency. Converting the array to a hash set takes O(n), but the fast O(1) average lookup time ensures that the solution scales well with larger inputs. While it does use extra space for the hash set, this trade-off is justified by the significant performance improvement. For these reasons, the hash set approach is the recommended strategy: fast, efficient, and simple to implement. To solve this problem, we start by understanding the task. We are given an integer called original and a list of integers named nums. The goal is to repeatedly check if original exists in nums. If it does, we multiply original by 2 and continue the process until original is no longer found in the array. At that point, we return the final value of original. Now, when tackling this problem, we need to consider a few important constraints and edge cases. The array nums might be unsorted, contain duplicate values, or even include negative numbers. Some edge cases to think about include situations where nums is empty, where original starts as a very large or very small number, or where original is not present in the array at all. For our initial approach, we'll use a brute force method. This involves iterating through the array to check if original exists, multiplying it by 2 if found, and breaking out of the loop once it's no longer present. It's a straightforward way to solve the problem, but we'll explore potential improvements later on. Let's break the algorithm into detailed steps. First, we initialize the input values, original and nums. Then, we set up a while loop to repeatedly check if original exists in the list nums. To do this, we use the in operator, which tells us whether original is a member of the array. If it exists, we multiply original by 2 and continue the process. If it doesn't, we exit the loop. Finally, once the loop ends, we return the updated value of original. The flow of the algorithm is straightforward: start with the given original, check for its presence in nums, double it if found, and stop when it's no longer there. This process ensures that we iteratively update original until the condition is met. The brute force approach works well here because it's simple and easy to implement. It relies on the in operator for membership checks, which has a time complexity of O(n) for lists. While this is efficient for smaller arrays, we can optimize the solution further. By converting nums into a set, we can reduce the time complexity of membership checks from O(n) to O(1). Although pre-processing the list into a set has an upfront cost of O(n), it can significantly improve performance when there are many iterations. Another important consideration is edge case handling. If nums is empty, the algorithm exits the loop immediately and returns the initial value of original, since no updates are needed. Similarly, if original is not found in nums at all, the algorithm still behaves correctly by returning the unchanged original. These insights help us understand both the strengths and limitations of this approach. Finally, let's discuss the data structures and complexity analysis. The input array nums is central to the algorithm. If used directly as a list, membership checks have a time complexity of O(n). However, converting nums into a set optimizes these checks to O(1), making the algorithm more efficient. The variable original is also key, as it keeps track of the current value being checked and updated during each iteration. In terms of time complexity, the brute force approach without optimizations performs O(n) membership checks for each iteration, and the number of iterations depends on the logarithm of the maximum value divided by the initial original. With optimizations using a set, membership checks become O(1), with a pre-processing cost of O(n). For space complexity, the unoptimized version requires O(1) additional space, while the optimized version using a set requires O(n) extra space. These trade-offs highlight the importance of choosing the right data structure for performance improvements. This solution begins by converting the input list nums into a set, which allows for O(1) average time complexity for lookups. This is crucial for efficient handling of repeated checks for the presence of the original value in the array. Next, the algorithm enters a while loop, where it checks whether the current value of original exists in the set. If it does, the value of original is doubled. This process repeats until original is no longer found in the set. Finally, the function returns the last computed value of original, which is the result. The use of a set significantly optimizes the solution compared to direct list lookups, particularly for large input sizes. The algorithm is efficient, with a time complexity of O(n) for the initial set creation and O log max_value for the doubling process, where max_value is the largest possible value of original during execution. This is the Java implementation of LeetCode problem number 2154, keep multiplying found values by 2. The solution mirrors the logic of the Python implementation. It uses a hash set for efficient O(1) lookups to determine if the current value exists in the array. The method iteratively multiplies the original value by 2 until it is no longer found in the set. Key differences include explicit type declarations in Java and the use of Java's hash set instead of Python's set for storing unique elements. To solve this problem efficiently, we start by converting the input array into a set. This allows us to perform constant time lookups, which is crucial since we need to repeatedly check for the presence of values. For the first example, the input array is nums equals 5, 3, 6, 1. When we convert it to a set, we get number_set equals 1, 3, 5, 6. Now, the initial value of original is 3. We check if 3 exists in number_set, and it does. So, we multiply original by 2, updating its value to 6. We then check the new value of original, which is 6, and find that it also exists in the set. Again, we multiply original by 2, resulting in 12. At this point, we check for 12 in the set, but it's not found. This means we exit the loop and return the value of original, which is now 12. In the second example, we begin with the input array nums equals 2, 7, 9, 4. Converting this into a set gives us number_set equals 2, 4, 7, 9. The initial value of original is 4. We check if 4 is in the set, and since it is, we multiply original by 2, updating its value to 8. Now, we check for 8 in the set, but it's not present. At this point, we can exit the loop and return the final value of original, which is 8. This demonstrates that the process stops as soon as a value is no longer found in the set, making it efficient for cases where the sequence terminates early. In the third and final example, the input array is nums equals 1, 10, 100. Converting this to a set results in number_set equals 1, 10, 100. Here, the initial value of original is 5. When we check if 5 exists in number_set, we find that it does not. This means there's no need to perform any multiplications, and we exit the loop immediately. The value of original remains unchanged at 5, and that is the result we return. This example highlights the scenario where the initial value of original is not found in the set, leading to an immediate termination of the process. When analyzing the time complexity of this algorithm, we start with the set construction. Converting the input array nums into a set ensures that we have unique elements, and this process requires O(n) time because each of the n elements needs to be hashed and inserted into the set. Next, we consider the while loop. The loop continues iterating as long as the current value of original exists in the set. Each iteration involves an O(1) lookup in the set, which is efficient due to the average constant time complexity of hash-based operations. Additionally, the value of original is doubled in each iteration. In the worst-case scenario, the loop will repeat until original exceeds the largest value in the input array, which we denote as max_val. The number of iterations required for this doubling is approximately log 2, max_val/original, which we can call k. By combining these components, the overall time complexity is determined. In the best case, when the loop doesn't execute, the complexity is O(n). In the worst case, it's O(n plus k), where k is the number of iterations in the loop. However, since k is often small compared to n, the overall time complexity can typically be approximated as O(n). Now, let's look at the space complexity. The main contributor to the space usage is the number_set, which stores all unique elements from the input array. In the worst case, where all n elements are unique, the set requires O(n) space. Beyond this, the algorithm uses only a constant amount of additional space for variables like original and the loop counter. These auxiliary variables require O(1) space. Putting it all together, the total space complexity is dominated by the set storage, which means it is O(n). This is an efficient use of space considering the operations we need to perform. When comparing this optimized solution to a naive approach, the performance improvement becomes clear. A brute force method might involve repeatedly scanning the array nums to check if original exists. Since each scan would take O(n) time, and the loop could run up to k times, the total time complexity would be O(n*k). This is significantly less efficient than the optimized approach. By using a set to enable O(1) lookups, the time complexity of each iteration is reduced from O(n) to O(1). As a result, the total time complexity becomes O(n plus k). While the space complexity increases to O(n), due to the use of the set, this trade-off is acceptable because of the substantial gains in time efficiency. To summarize, the set construction takes O(n) time, each lookup and multiplication in the loop is O(1), and the loop iterates a maximum of log 2, max_val/original, times. This gives us a final time complexity of O(n plus k), and a space complexity of O(n), making the algorithm far more efficient than a naive solution that scans the array repeatedly. In this section, we'll explore some common mistakes to avoid when tackling this problem. First, skipping the sorting step when it's necessary can lead to incorrect results. For example, if the solution relies on finding sequences or intervals, an unsorted array can cause repeated scans and unnecessary complexity. Sorting the array upfront can simplify the logic, making it easier to work with cumulative modifications. Next, relying on inefficient search methods, like linear search, becomes problematic as the array size grows. For large inputs, say 10 to the power of 5 elements, this can result in significant delays. Instead, using a set or hash map ensures O(1) average time lookups, which is much faster. Lastly, overlooking edge cases is a frequent pitfall. Scenarios like an empty array, duplicate values in nums, or handling original when it's 0 should always be accounted for. For instance, failing to address an input of nums equals and original equals 1 could cause the program to crash. Always consider these edge cases during testing to ensure robustness. Another mistake to watch for is creating infinite loops in brute force solutions. This often happens when the original value isn't updated correctly or the loop exit condition is poorly defined. Without proper checks, the program can keep looping indefinitely. To prevent this, always double-check your loop logic and ensure there's a clear condition to terminate. Additionally, ignoring problem constraints can lead to trouble. Constraints often specify the range of values for nums and original, and failing to respect these can result in performance or memory issues, especially with large inputs. For example, not accounting for extreme values can break your solution in edge cases. Always adhere to the given constraints and test extensively with boundary conditions to ensure your code remains efficient and reliable. When preparing for interviews, there are a few insights to keep in mind. First, optimization patterns are key. Recognizing when brute force is inefficient and replacing it with data structures like sets for faster lookups demonstrates a strong understanding of the problem. Be ready to answer follow-up questions, such as how your solution scales with larger inputs or how you'd adapt it for variations, like incrementing original instead of multiplying it. Debugging skills are another area interviewers focus on. Clearly explaining how you handle edge cases and runtime complexity can leave a positive impression. Lastly, always be aware of time complexity. While brute force solutions often have O(n)² complexity due to nested loops, using sets or hash maps can optimize this to O(n). To deepen your understanding, you can explore related problems like LeetCode 1346, which involves checking for the presence of doubled elements, or LeetCode 202, where transformations are repeatedly applied until a condition is met. These problems share similar patterns and can help you build transferable skills. Now let's consider some alternative approaches to solving this problem. A sorting in binary search combination is one option. While sorting the array has a time complexity of O(n) log n, it allows you to use binary search for O log n lookups, reducing the repetitive search costs. This trade-off works well when nums is large but original remains small. Another efficient approach is converting the array into a set for fast lookups. Although this requires O(n) time to create the set, it enables O(1) average time searches, making it optimal for large and unsorted arrays. For a more structured method, the two-pointer technique can be effective after sorting. This strategy minimizes redundant checks but might be unnecessary for simpler variations. Finally, a recursive approach can offer an elegant solution. However, deep recursion risks stack overflow, so iterative methods are typically preferred unless recursion is explicitly required. Each of these approaches has its own trade-offs, and the best choice depends on the specific constraints and requirements of the problem. Great work! Today, we covered problem number 2154 and explored how to efficiently solve it by leveraging key concepts like repeated checks and hash maps. Remember to focus on balancing simplicity and efficiency when designing your solutions. Thanks for watching, and we'll see you next time for another exciting problem. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!